Hello and welcome to the video. Today we're going to be writing a C++ library for Python. So let's start with why you might want to do that. A lot of, one of the complaints that Python gets is that it's relatively slow. And it's not necessarily slow on a normal human timescale. If you're just running Python, some kind of interactive script, you're never going to notice slowness. But if you're doing something that requires processing a lot of data, something that we run into quite a bit with reinforcement learning and other AI tasks, it's actually a lot faster to do those things in a language, a non-Python language. And if you're stopping and asking yourself, well, wait a minute, I've done all my AI deep learning projects in Python. Well, you have, but what's going on under the hood there is Python is calling back to a C++ library for a lot of those more data intensive, heavier tasks with the usual deep learning frameworks. So what we're going to do is we're going to build a couple of scripts. We're going to be using the Fibonacci sequence. In fact, a relatively inefficient method of calculating Fibonacci in order to get something that's nice and long running that'll really let us compare the speed of the two languages. So let's go ahead and start off with our Fibonacci.py. All right. So in Fibonacci.py, and I'm making the assumption that you're on Linux. Obviously, you could do all of this on Windows as well, but the commands that I'm running will work with a Linux installation. I'm also making the assumption that you're already capable of running both Python and C++ independently, that you have the compiler set up. There's nothing to stop you from still going through this tutorial and just setting tools up as you need them, but I'm not going to cover the tool setup side of things. All right, let's go ahead and jump in. So Fibonacci.py, we're going to import datetime, and we're going to define a Fibonacci function. And this is nothing special. I basically stole it off the guide to the publicly posted Fibonacci function documentation. So if n is less than or equal to 1, go ahead and return n. Otherwise, we're going to call the Fibonacci function again recursively with n minus 2 plus Fibonacci n minus 1. And then down in the actual execution, we're going to say if name is equal to main, also with underscores. Then we're going to set n is equal to 10. We're going to go ahead and capture the time. So we're going to say time at t1 equals datetime dot now. Fib is equal to Fibonacci with n, and t2 is equal to datetime dot now. All right, and then we're going to capture the time delta is equal to t2 minus t1 dot total seconds, and then we want the milliseconds, so we're going to multiply it by 1,000. All right, and then we're going to say print calculated the nth number of the Fibonacci sequence as fib. Print operation took approximately time delta milliseconds. All right, and that is all there is to our Python function. Let's go ahead and run it and see Yep, I definitely missed something. Up here, I returned nothing. I just said return. And that's not going to work. So let's return n. Let's try it again. All right. Except that did not quite 0.01 milliseconds. All right, let's expand that out a little bit to 50. Fibonacci calculations are very, very fast with small numbers, and then tend to get very, very slow as it increases exponentially in complexity as we get to larger numbers. So we're going to leave that running, and we're going to go write the C++ version of this. So we're going to call this Fibonacci.cbp. And we are going to include IOStream. And we're going to include chrono. And then we're going to declare a float. And this will round a little bit in our use case, but that's okay for what we're doing. I'm way less, I'm more interested in sort of total time and complexity than I am in, it displaying properly in all scenarios. All right, if n is less than or equal to 1, so basically the same logic, just in C++, return n, return Fibonacci n minus 1. Plus Fibonacci n minus 2. And then down here, we're going to say int main is int argc char star star argv. And then we're going to declare a few namespaces. We're going to say using std chrono high resolution clock. We're going to use that in a moment. We're going to say using std chrono duration cast, using std chrono duration, and then using std chrono milliseconds. Okay. We will be saying int, or actually we'll go ahead and make it a float. Float n is equal to 50. And then we'll grab our time. Auto T1 is equal to high resolution clock now. Float fib is equal to Fibonacci n. And then auto T2 is equal to high resolution clock now as well. And then we can go ahead and grab our time delta. So auto time delta equals duration cast in milliseconds and T2 minus T1. Okay. And then here we're going to say std cout final number in the Fibonacci sequence is fib std endl, and then we're going to say std : cout operation took approximately, nope, need our left arrows in the right place, time delta dot count, and milliseconds, if I can spell that. And then we'll pass in an std endl. All right, So obviously if your IDE is set up for C++, you can just compile this. I'm going to compile it over here in my terminal so you can see how that's done. So we're going to use G++. So we're going to say G++ Fibonacci.cpp -o and Fibonacci. Okay, and now if I run that, it should, we hard-coded in 50, so it should go get us the duration of 50. And let's come back and we can see Python is still running. It's still trying to do its thing. And this is where I said your time complexity gets quite a bit higher as you go, you know, up in numbers. All right, I paused the video there for a second, but C++ came back with 74,000 milliseconds, and you can see that Python is still thinking about it, even though it's the same logic. So obviously, and we'll get the time when we, when this eventually finishes, but obviously the goal here is to get that that C++ speed over here in our Python program. And then and this is, again, this is important when you're dealing with large data. Maybe you're dealing with training. I guarantee you a lot of the RL libraries, things like PyTorch, probably have a bunch of C++ components. They're not doing all of that processing directly in Python. So one of the things that you need to do, and I've already done it, but you will need to install apt install pybind11-dev. That's going to be an apt installation. And then we also need a requirements.txt at this point. And this is going to include pybind11 and Python select interpreter. In this case, I already have a Python C integration environment, but conda activate. Okay. So I can do a pip install -r requirements.txt, and what we should see here is, yep, requirement already satisfied. So you need one pip package, and then you need your apt install pybind11-dev to get this working. And obviously, if you're using a if you're using a Red Hat based system, that's probably yum install. Change that to your package manager of choice. So let's go ahead and work on the Fibonacci lib. So we're going to create a new file called Fibonacci lib.cpp. And we're going to include pybind11 /pybind11.h. Namespace pi is equal to pybind11. All right. And then really we're just going to come over here to our Fibonacci. And that really doesn't need to change. And then we can call, in all caps, pybind11 module. And that's going to be Fibonacci lib m. And we're going to do m.def Fibonacci. And then an ampersand. Get Fibonacci. And calculate, we'll give it a description. Calculate Fibonacci number. Okay, And what this is doing is this is basically going to expose, that PyBind module, or that this is going to expose this as something that Python can see. And obviously this is a really, really simple use case, but it works for what we're doing. Hey, Python finally finished. So by comparison, we ran our C++ Fibonacci in 74,000 milliseconds. We ran the Python version in 628,000 milliseconds. So this was almost 10 times as long. Python was almost 10 times as slow as running this in C++. So that's why we're doing what we're doing. All right. You'll notice we've got our little red squigglies here under Python pybind underscore module. If you are in, so we don't have a C++ properties.json yet. I'm going to go ahead and create a .vs code folder. And I'm going to copy this in. If you have the same problem as me, you are welcome to go grab this repository. I will post it in the video description as a reference. But basically, we need a properties that includes a path to the Python library here. Site packages pybind 11 include. So obviously, this is hard-coded to my home directory. You probably don't want to do that. It's also hard-coded to my library path. So there's probably a cleaner way to do this. And I would recommend tweaking it for your setup. But this should get us over here to a point where, here, that's just Fibonacci, not get Fibonacci. All right, that should get us to a point where we can, we no longer have it complaining about our lines here. All right, so we have our module definition. We need to go ahead and compile it into a shared library file. And this one is a little bit complicated, but stick with me. And again, there will be a reference to it in the README. C++ dash O3 dash wall with a capital W dash shared dash std equals C++ 17 dash F PIC dollar open paren Python 3 dash M pybind 11 dash dash includes Fibonacci lib.cpp dash O Fibonacci lib dollar Python 3 dash config dash dash extension dash suffix. And I think again we need there we go. All right. Except it's complaining again about there we go. All right, we have a working command. Again, that was a little bit painful. This one will be, this one's hard to type out in one go and succeed at. It will be in the README in the reference document. And just from a workflow perspective, I would never normally type out something like this, at least not more than once, as part of a regular workflow. What I would normally do here is I would have a tasks.json in VS Code, or the appropriate build task in whatever your editor of choice is, and then I would let the IDE handle it for me once I got the initial command working. That way you don't have to successfully type out a compile command like this every single time, or have successfully saved it somewhere. All right, let's go back to the fun stuff now that we've had that aside. We have at this point we have successfully compiled an SO file out of our Fibonacci lib.cpp. Now we need to go ahead and set up, we already called that one Fibonacci.py. So let's do Fibonacci from cpp.py. That sounds good. And we're basically just going to come over here and grab the full Fibonacci. We don't really need this as much anymore. We're going to go grab the full Fibonacci.py, and we're going to copy it over here. And we'll just delete that. And then what we'll do is we will just import Fibonacci _lib. And that's going to probably show some errors. Yeah, is not accessed. That's fine. We'll use it in a moment. And then down here, instead of Fibonacci, we'll do Fibonacci lib.fibonacci. And we really shouldn't need to make any other changes. Let's go ahead and let's run it with 10 and just make sure it works. All right, so yep, 10 worked in 0.01 milliseconds. Let's go do our 50. And that should take a little longer, but it should take, 60,000 or so milliseconds, not the 600,000 that Python was taking before. I'm going to go ahead and pause the video for a moment while this runs. All right, and we successfully ran the program in just under 40,000 milliseconds, which is just under 40 seconds. So instead of this taking, 600, 700,000 milliseconds, we're able to do that calculation in under 40 seconds because we are relying on C++ in the back end, and it is just drastically faster than Python. So a couple notes. This was obviously a really simple demo. There's a lot more to consider if you're packaging C++ up for use in a Python program. One of the big pros with C++ or with Python is that it's very portable. If you're running Python 12 or 3.12, you can run Python 3.12 basically anywhere that has the right packages. This is compiled and working on my machine. And if I was going to run it on many machines, I would want to make sure that it could compile successfully and I could deploy it as a shared library. So it's not like this isn't quite as portable, but it is a tool in the toolkit if you need something high performance. And if nothing else, it's an interesting look into some of the trade-offs that people are making with these larger projects. Is they're taking on more work, more complexity, in order to make something that is much, much, much faster for the end user. So with that, I'm going to go ahead and wrap up the video. If you got anything out of it, hit like, hit subscribe. I'd appreciate it. And until next time.